Welcome to the first lecture of today. Let's continue with this great event. It's a great pleasure for me to introduce Professor Felipe Linares. He is a full professor at INPA. Felipe is one of the main researchers in the field of the nonlinear dispersive equations. He has published more than 80 papers in internationally prestigious journals and with more than 2,000 citations. Felipe has 16 former PhD students and 5 postdoc supervisions. Felipe is one of the responsible for the dissemination of dispersive equations in Latin America. Today, Felipe will talk about the Cauchy problem for L2 critical generalized ZK equation in dimension 3. Thank you, Felipe.
Okay, thank you, Mikhail, for the introduction. And thank you for the organizing committee to invite me to give a talk in this conference. Okay, so today I would like to talk about one problem. I was working during the pandemic, right? It was in 2020 with João Pedro Ramos. Okay, so I think this is a good opportunity to let you know what we have done, and there are many problems, and probably you get interested in this. Okay, so the equation that we are going to talk about today is this one. It looks this is Sakharov-Kuznetsov type equation, right? So you have here is a real function u, and delta denotes the Laplacian that we know in the special variables. And the nonlinearity is kind of exotic. And I'm going to explain why this is so exotic. So the outline of the talk is the following. We're going to have a long motivation, many motivation to work for this equation. And then there's some main results, some remarks on the main results. The idea of the proof is going to be very fast. So it's a homework for you to go and look at the proof. And I'm going to mention several open problems regarding this equation. Okay, so as I mentioned before, this is a joint work with João Pedro Ramos. At the time, he was in the ETH in Zurich, and now he's in the EPFL in Lausanne. Okay, so I just started with this. It's recently Professor Sakharov died. This is probably 1 month ago. And I had the chance to meet these two guys. It's Sakharov-Kuznetsov in 2017 in the CIRM. Okay, so I was talking about some Sakharov-Kuznetsov equation stuff. This one that I talked today. All right. So this equation that I plan to mention today is a generalization of this one here, and this makes perfect sense, right? From the physical point of view. So you have again, this is a real function. Then you have delta as before. This is a Laplacian, and you can consider this equation either in 1 dimension, in 2 dimensions, 3 dimensions, and it makes sense, right? And it was what Sakharov-Kuznetsov derived as a long wave small amplitude limits of the Euler-Poisson system, okay, in this called plasma approximation. And at the time, it was a formal derivation of this long wave limit. And in some moment, with David Lanz and Closov, we make this limit, we justify rigorously the limit for the equation there. Okay. So this equation is known from the point of view of symmetries of integrable equation. is no good in the sense that, well, it's not completely integrable. However, you have a Hamiltonian structure, and so you can have at least 3 conserved quantities. This is in L1, and then you have this L2 that is important for us, and this one in H1, okay, that is also important to extend. If we got a local solution in the right spaces, extend these local solutions globally. All right, so you can also say, well, this Sakharov equation, you can see it as a generalization, at least in the structure, for the Korteweg-de-Vries equation, but Korteweg-de-Vries equation appears as a propagation of nonlinear wave in shallow water, and we saw that the Sakharov-Kuznetsov appears in plasma physics, right? There is also in 2D a generalization that is interesting and appears everywhere in the literature. This is the KP equation, right? And there is the nonlinearity, the dispersive part is not local, right? So you have this operator that is defined via Fourier transform in this form, right? So you can have something, so generalization of KDV. In 2D, you can think on Sakharov-Kuznetsov equation, you can think on KP equation, right? So the solution that we are interested here are in the following sense. So we are looking at the problem, right? So you have a dispersive operator P, and then you have a nonlinearity that includes not only U, but a derivative, right? And well-postness is going to be in the sense of cat. That means you have initial data in a functional space, and then the corresponding solution describe a continuous curve in that space, right? So what we are saying is that if we started in this space X, then U is going to be continuous in that space, okay? And so this is different in general, but what we have for nonlinear problem, right? Because in general we have existence, uniqueness, continuous dependence, but then the space where the initial data and the solutions are not necessarily equal, right? Okay, so but we are asking to remain in the same space, right? And if we can prove that the solution that we have for any time, then we can say that this solution is globally in time, or this initial value problem is globally well posed, right? Then the natural space to work with dispersive equation is always Sobolev space in base 2. So we are looking at solutions with initial data in HS, in RD, right? And this is the definition where we say that this is distributions in RD, such that this operator remains in L2. Okay. Okay, so to start to work with this, I want to prove local well-postness. I would like to guess what should be the correct space, right? And one way to do it is, well, in the case that you have a dispersion that is homogeneous, right? You can use a scale argument, right? So you can see that you have a solution of the initial value problem associated to the CK equation. Then for lambda positive, this is also a solution with initial data, this one over here. So performing just a Fourier transform, you can find this equality here, and then we may have solutions whenever S is greater or equal than this number, okay, the number given by that. And this is the critical space for the nonlinearity K, right? And then this is what we hope to have as a goal, right? So I started in HS. I would like to prove local well-postness until this regularity Sk equal to the dimension divided by 2 minus 2 divided by k. All right? Okay. So let's talk a little bit about the history of local well-posted for this Sakharov goodness of equation in the case that you have nonlinearity with k and positive integer, right? So you started with the Sakharov goodness of equation in 2D, and the first work was done by Faminsky. So in that case, he considered S integer, right? And he proved local well-postedness in H1, for instance, right? And the method that he proved is combined smoothing estimates and contraction mapping principle. Okay, so in that case, you have local well-postedness in HS is an integer. Then in 2009, in collaboration with Ademir Pastor, we extended the result of Faminsky using what was done for the KDB equation by Kenny, Ponce, and Vega. And we obtained a result, local result in HS for S greater than 3. Okay, since then, there are many people got interested in this problem. And then there was a major improvement in 2015, independently, Molinet and Pilot, Grunrock and Hare obtained local well-postedness in HS S greater than 1/2. Both of these two groups use Fourier restriction data. And what we notice next is that in the previous result, we have local solutions in S greater or equal than 1. So in particular, we can use the conserved quantity that I showed before to obtain a priori estimates and then obtain global solutions in HS for any S greater or equal than 1. And then in 2018, it was recently at the time, Kinoshita obtained the best possible result for using Picard method or contraction principle, right? So he proved that the local theory can be obtained in HS S greater than -1/4, right? But then, so he was working with the sharp bilinear estimates, okay, as Molinet, Pilot, Grunrock, and Hare. But then he introduced a new refined analysis, a very nice idea that is this Loomis-Whitney inequality. Okay, so in particular, the local result of Kinoshita, that is S greater than -1/4, give a global result for any S greater or equal than 2. Then we move to still the CK when K is greater or equal than 2. So we are thinking on the nonlinearity UX, right? UK, K greater or equal than 2. And then if we go back to the guessing of the regularity of the solution for that problem, we see that Sk should be 1 minus 2 divided by K. Okay, so we got that's what we got guessing the largest space where we can have a local solution. Okay. So in that case, we can find the result by Ribot and Bento in 2012 for any K greater or equal than 4. So this is a sharp result. That means the result reach this value. Okay. In 2015, you obtain this result by Grunrock, and this is S greater than 1/3. In the case of again K equal to 2, right? This is called the modified Sakharov-Kuznetsov equation. The best result obtained was S greater than 1/4, first by Ribot and Bento, and Kinoshita pushed this to S greater or equal than 1/4. Okay, even though you can see that what you expect in that case should be L2, right? Recently, you have this Basha Yarda, Farah, and Rudenko proof that this result, the global result for this modified Sahara Kuznetsov can go down to S greater than 3/4. All right. Okay, so now we move to the 3D problem and we go for Sakharov-Kuznetsov. In that case, you can find a result by Ribot and Bento, and this is local well-postness in HS S greater than 1. And there was a previous result in collaboration with Jean Clouseau below, above 3/2, right? And then Molinet and Pilot prove that you can have global solutions in this 3D case for any S greater than 1. Herr and Kinoshita in 2020 established optimal local well-postness by using the Picard iteration, right? For data in HS S greater than -1/2. And then they also obtain global well-postness for S greater or equal than 0. Right? Next, we move to the case K greater or equal than 3. And the results are given by Grunrock, right? And for any S greater than 3/2 minus 2/k, this is K greater or equal than 3. For the case K equal to 2, it was particularly addressed by Grunrock in 2014 and Kinoshita in 2019. And they obtained locally results in either case for S greater than 1/2. Okay. And then there was a little bit, Kinoshita could go a little bit down, and then he established that result in S equal 1/2. All right. Okay. So when I before I talk about the global well-postness, right? And then we had to be careful when we said, well, local well-postness for any data or just for some data. So I would like to retake the conserved quantity that I show in the 4 slide and see what is the a priori estimate that we can get, right? So for instance, in K in dimension 2, K equal to 2, right? So in that case, you have this conserved quantity that is L2, and then you have this energy that gives you, that makes sense if you are in H1, right? Okay, so you can obtain an a priori estimate using a Gallardo-Nirenberg inequality. You're gonna get a sharp 1 Gallardo-Nirenberg inequality, and then you can obtain this inequality there, right? And then there is a Q there that is only the unique solution of that elliptic equation, right? So it's a ground state, and it coincides with when you are working with Schrodinger equation. So it's exactly the same equation. Okay, so you got this estimate, and you can see that this coefficient in front of the gradient of U on the right-hand side is smaller than 1, then you can obtain an a priori estimate, right? So that means if the initial data, right, in L2 is smaller than this number, then you can obtain a global solution, right, for your problem. Okay. Otherwise, you don't know. But fortunately, there is a result by Farah, Holmes, Rudenko and Yang, that they show that this initial value problem associated to the modified Sakharov-Kuznetsov equation in 2D, then you get a blow up infinite or infinite time, and that the result is inspired by the results obtained by Martel and Mayer for the critical KDE equation. Okay, so global solutions for k greater or equal than 2 depend on the size of the initial data. Okay, so you can have local solution for any data, but then to extend the solution, you have to look at the conserved quantity and say something about that. Okay, and in that case, in this particular case in 2D, this equation is 2D critical in the sense that this is the highest, or the highest, no, the largest space where you can have a solution, right? And I'm gonna give you some reasons for mention that this is a critical problem, right? Okay, so after seeing all this result here, okay, we can go back to 3D, and we can see that in the case of, in that case, you don't have any powers, integer power, that makes L2, right? The largest space where you can solve the problem. Okay? So what we did was, well, let's see. Let's consider k to be a real number. And then we go back to the scale argument, right? And then we found that k has to be like the one that we mentioned in the first slides. It should be 7/3, right? And that makes sense, right? So u can be positive, negative. You don't have any restriction on that. And you may try to study that equation. And that's what we did. Right? So, and what is, so the point to say that this is a critical equation, right? L2 critical. And they say, well, this is not only because of this, the largest resolution space is L2, but also because the nonlinearity is borderline, right, to impose global solutions, right? So you started, that's what was the motivation to do this a priori estimate. So you saw that in that case, you have a critical CK equation in dimension 2, and in order to have a global solution, you have to have a restriction in L2. So the same happens in dimension 3 if we consider the equation that we are talking today, right? And not only because of that, we can say that this is critical, but also because you can have this solitary wave solution, right? And solitary wave solutions, you can identify if they are stable or unstable. So in the case of the critical CK3D with this power 7.3, there is a result by Underwood, and they say that these are stable if k is less than 4/3, and unstable if k is 4/3. And I guess since k equal to 4/3, there is no proof of that this is unstable. It should be. Okay. So that's all this fact that we mentioned before motivate us to work in this initial value problem, right? And then the first step, as always, is to establish local well-posedness, and then try to see if we can extend this local solution globally. Okay. So in the works that we mentioned before, there are many techniques, many improvement and new arguments, but they really don't apply directly to this equation that we are concerned with, right? And so what we try to do is, well, combine the experience that we have with this generalized CK and see what we can say about this new equation. Okay, so the local results that you will see is you started in initial data in HS only between 3/4 and 1. We can obtain a global, a local solution that is continuous in the sense of it's continuous and is satisfy the Cato definition of well-postness. And then to do that, we need some other norms to obtain the uniqueness of that problem. Okay, so we have existence, we have uniqueness, and also this application that is important for the next results is locally Lipschitz continuous. Okay, and this is for free because we are using a contraction mapping principle. All right, so then what method we can apply here? So we are trying to apply methods that give us any information between what happened between 1 and 2, right? And those methods were introduced by Ribot and Bento. Okay, so you can use Ribot and Bento arguments that I'm going to mention before, after, in a while. And then there are some other methods introduced by Grunrock, okay, when you have k equal to 2. So the point, so the difficulty, as you can see, is you have to deal with this nonlinearity, right? And then the idea that we are using is coming from Ribot and Bento, where they use a paraproduct decomposition for the case that they were working. Okay, so this is what we do. So we construct almost paraproduct decomposition of this nonlinearity, right? And then we have a nonlinear lemma that make possible to obtain or to apply the contraction principle. All right, and that only works in this interval 3/4 to 1. And this is very curious because in general, you can have S greater than 3/4 and you don't stop, right? Like in this case. All right, so let's keep doing this. And what is the problem in those estimates? Well, we're going to use a localization in frequencies, right? And then when you compute the sums in S equal to 1, this maximal estimate is going to blow up. Okay, so we have only control if S is smaller than 1. Okay, still we try to say, well, we can do something else and go and complete the whole picture at least to 2. And then, well, we go to this nonlinear lemma. And from the nonlinear lemma, this is good. For low frequencies, you can go and then instead to estimate the gradient, you can estimate the Laplacian. But again, you stay short, right? And then we cannot use the contraction mapping principle. Okay, so we can use compactness in order to obtain this result. Okay, so this is almost well-postness, and I'm going to tell you what is that. Okay, so what we have is we don't have local, we don't have continuous dependence, right? So we can use compactness to have a solution that is unique in a space that is so we have the same regularity as we started, but we don't have continuous dependence to finish with the local well-postness, right? So what we did was, well, if we are in this interval, right? So we have the regularity that we expect, intersection with some spaces here, okay? So we are doing this for any R, for each R in this interval, right? So we construct a solution there. And this is nice in the sense that it's unique, right? And has the same regularity. And that is going to let us to do something else. Okay, so with that lemma, we can obtain the following. So we have a solution, right? This unique solution is here, is bounded, it's only in infinity, right? And then the spaces that we have constructed to get the regularity as in the previous case come from this intersection, right? And then we are doing this. This is very fancy, but anyway. And what we know that it's, if we are close in HS, we can say that we are close in these spaces, okay? And then we don't have a local well-postness in the sense that I mentioned before, but we still have this solution that is going to help us in other problems. So then, in particular, we started with initial data here. Then the solution of the initial value problem 1 belongs to this space, right? And then you have that. This is the only thing that we know. Okay, so there is no continuous dependence in this interval here. Okay, that's not what we want to do. All right, so the remark that we have here is that the data solution is fine in 3-4-1, right? But then after that, we don't have continuous dependence, right? But we don't lose regularity for the solution that we found. And of course, you can say, well, but this is not so good, right? This is like you have a solution that is in S between 3/4 and 2, right? And then it's far from B, the critical one, right? It is in L2. And then we remember that when you touch the critical point and you ask for the continuous dependence to be more than continuous dependence, we can see that we cannot do anything better than that, right? If S is less or equal than C. Okay. All right, so. But still, we can do something for the global results, right? So we have a local solution. There is no continuous dependence in some range, but still we can consider or we can obtain global solution in this case, okay? So with the compactness result that we got in theorem 2, so we can guarantee that the conserved quantity makes sense, okay? So this is important, right? Because you have conserved quantity and in general, you deduce this conserved quantity because you have regularity, right? It's not like, well, I have a solution and put in there and that's it. No, you have to integrate by parts and justify everything to get these nice conserved quantities M and E, right? And then, because we have the right regularity, we have that this makes sense, right? And this also makes sense. And so we can use these two quantities in order to get a priori estimate, and then we get a solution for a small data. Okay, so we got the second main result on this work with Joan is that we started with the initial data in H1, right? Then we have a global solution whenever the initial data in the norm of the initial data in L2 is sufficiently small. Okay, and so we have a solution that is bounded and continuous in H1, right? And so this is okay. This is what we expect, right? According to the argument that I was mentioned before for the a priori estimate, combining H1 and L2. And then we have a global solution whenever the initial data, the norm of the initial data in L2 is less than the norm of the ground state associated to the equation, right? So in this case, we get it for a small solution, and so the conjecture is it should be less the norm of the initial data in L2 should be less than the solution of the ground state in L2, right? All right, so now I want to tell you one more thing about this solution that we have. And there is an interesting problem in harmonic analysis that it was raised by Carlson in the context of Schrödinger operator. So the question was for which S, right? This is the linear case for the Schrödinger equation. So when this limit realized almost everywhere in X, okay? So this is, he showed that this is true if you started with initial data in H1 fourths, n equal to 1, and it opens, I think, a room to understand this problem and to obtain results, right? And then this is not only for the linear problem, but also for the nonlinear problem. In that concern, if we look at the solution that we obtained, we saw that Copan, Luca, and Stafilari, they obtained or they propose a method that gives you pointwise convergence for the flow, right? In the nonlinear case. Okay, so you got a solution of the initial value problem, right? And then you can prove in our case that this is true. Okay, and this is the main tool that we use in addition to the argument of Compan and Luca and Stefanelli is the L4 maximal function established by Grunwald. Okay, so this is nonlinear, it's a nonlinear result. Okay, so now is the technical part. And of course, you may guess that it should be very technical, and it's true. And then what we do is just we localize, right? In order to get a paraproduct for the nonlinearity that we are dealing with. Okay, so this is the usual way to use a little tail decomposition, right? So you define the projections, right? And then with those, we can have this equivalent. This is equivalent to work in the HS norm, and that's why. So we localize this, and we try to obtain all the estimates in terms of this S norm, right? Okay, next. Okay, so the people that is familiar with what Katie, Ponce, and Vega did, they try to extract some information for the linear problem, right? So establish, for instance, the smoothing effect, right? Kato type smoothing effect. Then you have a maximal function estimate that this is no good for, as you see here, we have a problem with S is equal to 1. And then a stricter estimate. Okay, so we combine these norms to prove a contraction mapping principle, right, in the correct space. And this is what we do, right? So we define this as T space that appears in the statement of the theorem, and it's given by Sobolev, a smoothing effect, maximal function estimates, and a streak. And then in the middle of the computation, sometimes we get better than this, right? And that's happened if K is positive, and then we have to deal with different norms that include the derivative, right? Over here. Okay. So as I mentioned before, you have to look at this linear problem. You have the solution of that linear problem, and then you have this smoothing effect that we can prove exactly the same way for CK. This is a CK as before, right? We have in 2-dimension and 3-dimension are the same. Next, we have a maximal function estimate. So you have t between 0 and 1. This is nice. But then when you do this for s greater than 1/2, you have some problems. And this is based in the proof given by Ribot and Bent. All right. And then we have L2, L4 Stricker estimates. So we started with initial data in L2. The solution is in a better space in all the variables x, y, and t. Right, so next we have to have the estimate for the no homogeneous part. And we see the first estimate that they were proved by Ribot and Bento. You have this first estimate that is just regards with the smoothing effect. Oh, this is the dual of the smoothing effect. Then you have the double smoothing effect, like this. And you have this estimate for the maximal function, estimates the non-homogeneous part of the Duhamel part. Okay. And then we need this retarded Stricker estimate. This is L2, L4. So we got the homogeneous one, and the non-homogeneous is this one over here, right? And this is, we follow the argument by Bao-Qian, Ligia, and Xunyan, and they extend this famous Kiselev lemma, right, that work for other dispersive equation, right? I just want to mention that this was proof of these guys. All right, so, okay, so what is the next step? Is, well, we want to prove for local well-postness. We are considering S in 3-4-1. We define the equivalent integral equations, right, associated to the equation that we are working with. This one here. And then we define a ball in this space. Okay, so you are in this space with this size, with all the norms that I mentioned before. And then the linear part is okay. Okay, this is, and then the hard work is for the nonlinear part. Okay, so in that case, just to save energy, instead to do this, the whole argument for this one is exactly to do the same argument for the difference of these two. Okay, so because in this, if we do these estimates, what we prove is that the application is well defined, and this one is used to prove that this you have a fixed point, right? And so we work with this, and we get this for free. All right, but the whole point is this one. Okay, so we have all the estimates. So if we go back to the estimate I mentioned before, the retarded estimate, you end up with this. Okay, so you have to bound this in small L2 in the natural numbers, right? Following the idea of Ribot. So in the case that they work, they have a modified Sakharov-Kuznetsov equation, and they got a beautiful formula. This is very nice. Okay, so you have U squared, you can rewrite it using the projections in this way, and start to do estimates. So in our case, we have this guy is a fraction, right? But then we construct something similar to this one. Okay, and that's the main thing. It's like we have this nonlinear lemma that I mentioned before, and we obtain this inequality here that is involve all the estimate that we are concerned with, right? So this is the main thing to obtain this nonlinear lemma, and then the restriction that we have are coming from the maximum function estimate and not for this here. Then I'm just gonna give you a line to look at the paraproduct that we are taking on. So we play with calculus here, and then we rewrite this expression, right, as Ribot-Bento did. And then we have explicitly this the face of this object over here. Okay, so I'm not gonna give any detail because it's yes, it's too much. All right, so with that, we can conclude that we have a solution, right, in this interval S between 3/4 and 5. Okay, and then the application data solution is glitchy because we are using contraction. All right. Okay, so to end, there are many things to do. Okay, so starting with the local well-postness, we would like to have to extend this in the Kato sense, right? S greater or equal than 1, right? And of course, if we can go below 3/4 to 0, that would be nice too. Global well-postness in H1. And then, as I mentioned before, the conjecture should be the L2 norm of the initial data is smaller than the L2 norm of the ground state. And then if you get that, then you may be interested in see if you get a globe, and then you may try this using either the idea of Martin-Mer or Kenny-Mer. And of course, after that, if you understand well the problem, you will like to see how are the dynamics of the globe. So this is one, a lot of things to do anyway. But then there are some other different directions, asymptotic behavioral solution, as Mendes, Munoz, Poblete, and Pozo did for the 2D CK equation. Then you can prove propagation regularity of solution, as Mendes did for the CK equation. Stability of soliton, as Cott, Munoz, Pilot, Simpson, and Frederick Valette did. And even unique continuation principle, as Cosetti, Fanelli, myself, or Bustamante, Jimenez. Okay, so thank you for your attention.
Thank you, Felipe, for this nice talk. Any questions or comments? Okay, any questions? Okay, let's thank Felipe once again for this talk.
Okay, thank you.
I'm sorry. Oops.
Professor Paula Cerejeiras, have a question?
I was asking if I could see a slide, but unfortunately I spoke too late. The slide when you make the regularization for your the attic regularization for your solution. I was just to confirm how the regularization was done, but you already closed your slides. I spoke too late, so my apologies.
Let me see. So tell me where.
It was when you were talking about the DJs, when you introduced the delta J's for your solutions, for your regularization. You have a smooth function. Yes. Yes, I think the previous, yes, that's exactly. So you make a regularization on the Fourier and you pull back. Okay, thank you very much.
Okay, no problem.
That's actually. What is that? Thank you.
Okay, no problem.
And also thank you for your clear lecture.
You're welcome. So I will stop to share the screen. Okay.
Yes, so Duvan, Juan, we continue with the next talk, right?
One moment. Welcome, Professor Boyan. Thank you very much for accepting our invitation.
Hello, hello. Do you hear me?
Yes.
Duvan?
I think we still have 9 minutes to go before
The already program is 10 hours. Is
Okay, so
1951. Horario programado es 10 horas. Estamos 9:51. Duvan?
I think maybe we can start in 10 minutes if you have no problems, just to follow our schedule.
Professor, your slide.
very good.
Excellent, excellent.
Ok, muy bien. El profesor Sousa.
Hello,
Entonces,
Duran.
hello. Hi, Professor Sousa. How are you?
I'm fine. You?
Very well. So you are going to chair the session of Professor Boyan Sirakov.
Yeah, that's it.
Thank you very much. So, Professor Sirakov, we are going to wait a couple of minutes, waiting for more people to connect.
Mhm.
Then I leave you, Professor Sousa, the session of Professor Sirakov. Thank you very much for your support.
Okay, thank you.
Professor Diego, I
Yes.
think if you want to start now, I think it's
Yes.
okay.
Okay, so please, Boyan, when you
One moment, Professor Boyan. 10 hours. Diego, Professor Boyan, está 10 hours.
yes, but
You
he's
listen.
not
2 minutes.
yes, we should wait a little bit.
Yes, 2 minutes.
Hello, Boyan. So can we start?
I'm ready.
Okay, perfect. So good morning, good afternoon, good evening, everyone. So let us receive and welcome Professor Boyan Sidakov. Professor Boyan Sidakov is a full professor at the PUC University in Rio de Janeiro. He defended his PhD in Paris 6, under the supervision of Professor Henri Beristic. And then he worked there in France as maître de conf at the Université Paris-Nanterre. And then he moved to Brazil, to the PUC University. And now he's a very recognized mathematician in the Brazilian and the international community. And he also coordinator of the graduate program in mathematics of the PUC Rio. And he also productive research in CNPq level 1A. And today he's going to talk about elliptic estimates with optimized constant and application to the qualitative theory of elliptic PDE. So thank you very much. You have the word.
Thank you very much too, and let me thank the organizers both for inviting me to this very interesting and strong conference, and even more to even organize that very interesting and strong conference. Well, so today today my goal is to tell you about ongoing recent works with Philippe Soufflet from Sorbonne University. On optimized constants in a number of basic inequalities in the theory of elliptic PDEs and some applications. I realize that most of the audience is not necessarily expert on the particular topics, but hopefully the talk will be understandable for a larger audience. So yeah. So to start with, the setting. So, well, the setting is think of a second order uniformly elliptic operator in divergence form. This is here the most general form of such operators. I will always keep the standard notations in such settings in most books, which are to call A the second order coefficient, B first order coefficients, and C zero order coefficients in an operator. And for such operators, consider weak solutions of a given equation. And think of coefficients, assumptions of the coefficients that guarantee either that solutions, I mean the Dirichlet problem, or just any solutions are locally bounded, and there is maximum principle that's valid for operators that have some coercivity properties, and also the Harnack inequality holds. And in some situations, we will assume a little bit more, what I call C1, which guarantees that by regularity theory, solutions of equations involving such operators have C1. Solutions. This is classical theory, for instance, described in a well-known book by Gilbert or many others. Also, instead of divergence form, we could consider operators that are in non-divergence form, or even fully nonlinear operators of Hamilton-Jacobi-Bellman or a Zix type, such as, for instance, Puch type extremal operators with lower order coefficients. And again, assuming sufficient integrability of the coefficients so that weak solutions, in this setting, this would be viscosity solutions, satisfy maximum principles and Harnack inequalities. Okay, so this is think of this as a basic setting where we are at. And well, I'm going to start first with an application, actually, this application that led us to realize that there were open problems of that type, and actually that made us realize that optimizing constants in some inequalities leads to interesting application. So the simple thing that I'm going to describe to you is a generalization, a classical generalization of the strong maximum principle. So the strong maximum principle is something that we teach in the PDE course, introductory PDE course, say for superharmonic functions. One can prove that if a superharmonic function attains the minimum, then it is a constant, right? That's what's written here. And another way of saying these linear operators is that if you have a subsolution which touches from your super solution of a given equation, then they must coincide this super solution. This is another way of saying expressing the strong maximum principle. So, well, this at first glance, and at least by its proofs, by classical proofs, is a sort of a linear result in the sense that we need a linear equation, or at least an equation with linear growth in the unknown function for it to hold. But let me show you a simple way of expressing that. So think of the operator level of u being just the proportion of u minus u. Okay, so then the strong maximum principle for that equation tells you that, okay, take a positive function which vanishes at some point, then there is no space under it to put its equation apart from the trivial zero function, right? If you have a positive, non-negative function which vanishes somewhere, there's no place to put it under its equation. Now replace this u here, this u on the right-hand side in this inequality, by some other function of u, which is a little bit bigger, say a polynomial, say a power. And now if we take a power which is more than 1, this is a little bit bigger, right? We small here. And then actually, no problem, there is enough space under u to the p to put a portion of a positive function that vanishes. And even it's just a power bigger than 2. It's C, more than C2 function that vanishes at that point. So actually, indeed, this seems to suggest that the result requires some sort of linearity. And that's actually not true. At 1984, Vasquez showed that the zero-order dependence, this u or up, actually it doesn't need to be Lipschitz, like it doesn't need to be like u. And precisely the result is as follows. Actually, there is a threshold for the validity of the strong maximum principle. And this threshold is strictly between u and powers of u more than 1. And the precise result is that actually what's necessary sufficient is that there is a dependence type of u here, which is such that 1 over square root of the primitive of f is divergent at, has a divergent integral at 0. Right? So of course, if f is linear, this is true, but there are no linear examples. And the main example for such functions that actually appears in applications is functions which are like s log s. And we may even have functions like s log s to the square. Up to s log s to a power which is more or equal than 2. All right. So yeah, this is essentially the functions that one may need in applications of applications of this result. Yeah. So, well, this theorem has seen a very large amount of work on extending its validity to weak solutions and various sorts of quasi-linear, fully nonlinear, singular degenerate elliptic operators. There's a whole book written by Patricia Pucci and James Herring on its validity for very general operators. But one property that, and essentially all proofs that were available of this result follow the classical scheme of the proof of the strong maximum principle that is usually taught in an introductory PDE course, which goes as follows. So first, we prove a weak maximum principle, the standard maximum principle for operators, say, with some coercivity, zero-order coefficient that has the right sign. Okay, then we construct a subsolution in an eduous. Usually it would be radial. For instance, for the Laplacian, it would be some translation and multiplication by constant fundamental solution in given annulus, which takes different values on the two sides of the boundary, and the normal derivative of this subsolution be non-zero. Then, by comparing this subsolution to your given supersolution, the supersolution also has a non-zero normal derivative, so you get the so-called Hopf-Lemma. And once the Hopf-Lemma is available, the strong maximum principle can be deduced by an analysis. I will continue to connect this. Well, the thing is that this construction of a subsolution, if you try now to generalize this to more general operators, this subsolution you would usually, you can only find some sort of radial one. So you require bounded coefficients simply to replace your coefficient by their bounds, obtain an operator with constant coefficients, and then write the corresponding radial variant, which is an ODE, and solve that ODE. Okay, that's the way it would usually go, of course. And this proof really requires bounded coefficients. So there was this ODE approach doesn't seem to have bounded coefficients. So there was the Vasquez type strong maximum principle was not known for operators on unbounded coefficients. And that's a theorem, for instance, that we proved with Philip a few years ago. That actually for operators that do have unbounded coefficients, such as I showed here, right? These coefficients C0, the C0 hypothesis here. So we may have only Lebesgue integrability and even a little less than that. Then the Vasquez strong maximum principle is valid not under the whole integral condition of Vasquez, which I remember here, but for nonlinearities which are such as the main example, which is as I said. So if this f doesn't grow more quickly than s log s to the square at 0, then the strong maximum principle is valid. Well, so what is the main ingredient of the proof of that thing? So it is the Harnack inequality, or more exactly, its variant for a super solution called the weak Harnack inequality, in which the constant would be optimized with respect to both to the domain, the size of the domain, and the norms of the coefficients of the operator, the first and zero order coefficients. Let me develop this now. Well, so first let's recall the weak Harnack inequality, right? This is also this is extremely fundamental result in the theory of parabolic PDEs. And this says the following: if we have a non-negative supersolution of some equation, then on a compact subset, we can bound from below the minimum of the function by some integral norm, right? Here, this epsilon depends only on dimension and probably ellipticity, and actually even for divergence for operators it depends only on dimension. You can take any epsilon down to n over n minus 2. And the constant, the CWH is weak Harnack, depends also on ellipticity and probably the Lebesgue scale and the bounds on the norms of the coefficients of the operator. And this is this B, C in R. Q and P are some numbers bigger than n or n over 2. And you can, to simplify, I think always of Q and P equal to infinity. It's going to be easier to follow. And the size of the domain you take. And with respect to this, C will be optimized. But yeah, let me just recall that this inequality goes back to De Giorgi. And the variant of it was used by him to prove, to end the proof in the 90s in the Hilbert conjecture. It was written, that's probably by Moser, then extended by Schrödinger for divergence form operators, and proved for non-divergence form operators by Kliwak and Caffarelli in the setting of viscosity solutions. Well, it's a quantification of the strong maximum principle, right? It tells you that if U is bigger than something somewhere, something positive somewhere, then U is strictly positive everywhere. And it's sort of a growth lemma, and it also implies the Hilbert regularity of solutions by a standard lemma. It has also a non-homogeneous version. You may have a super solution of an equation with right-hand side f, and then the price to pay is put some LP norm of f in the right-hand side of the equation. Yeah, so one of the optimization you need to do here is in the size of this BR here, because you see actually it's a little bit weird if P is infinity. I would say f is the function 1, then the infinity norm of 1 is always 1 in any BR, but the OP norms depend on R. So you can't really write it in this form if you want to optimize. You need some sort of local Lebesgue spaces. And yeah, this is just a little bit of technicity here, but if we take the uniformly local Lebesgue spaces defined as the maximum of LS norm in both of radius 1. And then this quantity here, and is the essential quantity, right? Well, it's the first order coefficient in the uniformly Lebesgue LQ space to some power, which is the right scaling, and same for the zero order coefficient, right? Think of Q and P equal to infinity, then beta Q is 1, and beta infinity is 1, and gamma infinity is 1/2, right? And then we have the important result that indeed the Weak-Harnack constant, that is CWH, is no more than exponential of m times the R, the size R. That it cannot be better than that is obvious. I mean, just write an ODE and you see that solutions are these exponentials, right? So it cannot be better than that. But what we prove for any operator in any situation is that it is indeed bounded by such an exponential. Right. So that's the optimal constant is exponential to MR, where M is this Lebesgue norm of the first and zero order coefficients. C0 is a constant which depends on this here bound and dimension. Okay, so yeah, this is, yeah, I'll just try to give very, very vague ideas of how this is approved. So once more, the inequality here, the same inequality I've written here, right, to start with. And what's the idea of the proof? Well, if you take a ball of size 1/m and rescale to a ball of size 1, you get an operator which has norms of coefficients which are also smaller than 1. So you essentially can use you get an equation in which you can apply the usual Harnack inequality because it's in domains of size 1 with coefficients of size 1. Then you scale back, then you do some optimal covering and a Harnack chain argument with optimized with respect to the geometry of the domain, and after some work you get to that inequality. Let me observe that there's also a counterpart of this inequality super solution, which I've written down here, which is the so-called local maximum principle, which says that the maximum of the function is bounded by some integral norm. And observe that for solutions we have both super and sub. So these two inequalities here give you the full Harnack inequality when they are combined, supremum of u smaller than constant time infimum of u. Right, so the local maximum principle also can be optimized with respect to the coefficients, and actually it turns out that the optimal constants there are not exponential but polynomial in them. Okay, so now once this is available, let me give you a vague idea of the proof of that extension of the strong maximum principle, the Vasquez extension of the strong maximum principle for operators with unbounded coefficients. So let's imagine, think of the Laplacian, doesn't matter, Laplacian and some function zero order term, which is like log u to a power times u. Well, then this log u to some power is like a zero order coefficient. The problem is that it can have an arbitrary growth because u goes to 0 at some point, and this log becomes infinite, and you don't actually control it because it depends on the solution itself, which is unknown. On the other hand, you have that inequality here. Of course, this doesn't make sense because the C may be infinite, but if this inequality down here made sense, what would happen in its right-hand side? Would have the minimum of u, which is 0 because u vanishes somewhere, times this exponential, which is infinity because this m is like some norm of C, which is infinite. So in that last inequality, the right-hand side is an indetermination of the form infinity times 0. So if you carefully approximate and work on it, it is possible to prove that in this infinity times zero, in this indetermination, the zero is stronger than the infinity, provided you have a smaller or equal than 2. So you get 0. The last product here, the exponential in the infinite is actually 0. So that's how one strong. And it is very different from that classical proof that I showed you with comparison to regular subsolutions, right? It's completely different proof, which works for operators with unbounded conditions. Right, so let me now, maybe a little bit of open problems here. First thing is that we proved the result, assuming this strong maximum principle, assuming that the nonlinearity behaves like u log u square, while Vasquez result for bounded coefficient works for the integral of 1 over square root of the primitive being infinite, which is a little bit more because you can admit u log u times log u and so on. And we do not know how to prove it under this more general integral hypothesis, which at first glance is quite an ODE one, so it's not completely clear how can one extend it. But it's also related to another upper problem, which is the following. We prove the strong maximum principle for nonlinear operator f of u by essentially linearizing, right? Would there be a Harnack inequality for the nonlinear equality itself? I mean, which directly somehow uses the structure of the function f of u. And that question in a very particular case was answered by Veseyurin, actually for solutions and a very specific equation, this one. And a full result of Harnack form is the following, that actually 1 over square root of the primitive infu to supu is bounded by a uniform constant. So another open question is it is possible to extend this result to different operators, for instance, non-divergence form, for instance. Well, okay, let me now switch to another problem we have been able to say something through the use of Harnack inequality with optimized constants. And that's the following, the so-called Landis conjecture. So a question that was asked by Kondratiev and Landis, these are two very well-known and important Soviet mathematicians that were at the base of the qualitative theory of PDEs in non-divergence form, in particular Landis, in the 70s. And one question they asked in a survey was the following, extremely simple thing actually. Just take like the Schrödinger operator, stationary solutions of the Schrödinger operator with a bounded potential in an unbounded domain of Rn, say some exterior domain, for instance. Is it true that solutions of that cannot decay super exponentially at infinity? Sense that if u goes to 0 more quickly than an exponential, is it true that u must be the 0 function? Or as I've written here, does there exist a constant which would depend only on the bound on the potential, such that the lim sup of exponential mxux this has to be positive? Right. Well, that extremely simple question is still open, very large. So even actually simpler variants of it are still open. Even if the solution is supposed to be defined in the whole space, even if we have entire solution, still is open. There's a little weaker conjecture by Carlos Koenig that solutions cannot decay, not like exponential, but like negative exponential to a power. This has been recently proved for n equal to 2 only. It's still open for n bigger than 2. And of course, there's a question of more general operators than just the Schrödinger operator. Right. So one thing is that originally the question was asked about even complex solutions in 2 dimensions. And very quickly, Meshkov proved that actually the answer is no. If you can assume complex solutions, then the optimal rate of decay is not exponential minus x, but exponential minus x to 4/3. And very strong mathematicians have contributed to this line of research ever since. Well, by using essentially Kahneman type estimates, which do not distinguish between real and complex solutions. So, well, the conjecture being open in the real case and people believe it's true cannot be proved by techniques which do not distinguish between real and complex solutions, simply because for complex solutions we know it's false. So that's one observation. Now, a few years ago, Carlos Kane, Luis Silvestri, as one, published a paper which actually restarted the interest in that sort of problems. And they proved that in 2 dimensions for some particular operators, the conjecture is actually true. And even sort of a fixed distance on each point on a sphere, there is a point in which, not the full conjecture, but the Koenig's conjecture, the weaker one, there we do not decay worse than R log R, exponential R log R. And this brought a number of generalizations. What's characteristic for all these words is that they work for 2 dimensions only and operations and equations in divergence form. And there is an important hypothesis, which is always hidden there, but which is always that the operator, we must make additional assumptions telling us that the maximum principle, or the comparison principle on any bounded domain, on any bounded subdomain of the space is satisfied. This is, for instance, the gain of 0 order coefficients that have a sum or something like that. This hypothesis is practically, nowadays practically all we know is under this hypothesis. Well, then Luca-Rossi in 2020 proved the full hypothesis, the full conjecture, but for operators in the non-divergence form, and again with the maximum principle on bounded subdomains, of course, provided the coefficients of the operator are bounded. And yeah, the method really uses the boundedness of the coefficients, the existence of very explicit subsolution, which actually is negative exponential. Well, recently too, there's a paper by 4 very strong mathematicians who proved, which is the only result up to now without the condition on validity of the maximum principle on bounded subdomains. In 2 dimensions, they prove that the Koenig's form of the conjecture is again true. The decay is no worse than x square root of log x. This is a hard paper, 2-dimensional, really, that uses quasi-conformal mapping, so really 2-dimensional. Higher dimensions is completely open. Results for unbounded coefficients in some situations were proved, but assuming integrability at infinity of the coefficient, which is a very strong hypothesis. And then actually one gets very strong results of the growth of the solutions, which are even exponential to a power smaller than 1. It's a little bit different line of study. And what we can prove by using the optimized Hermitian equality with Philippe is that actually the full conjecture is true for any operator, even with unbounded coefficients, provided that they satisfy this hypothesis of having maximum principle on bounded subdomains. Or another way of saying this maximum principle on bounded subdomains means that another way of saying that is the first eigenvalue of the operator is strictly positive for any bounded subdomain. And yeah, so actually we can go from bounded to unbounded coefficients. And that's another situation. It's similar to what's happening for this Vasquez-Strong maximum principle. So a result known only for bounded coefficients actually is proved to be valid through a different technique for operators that may have unbounded coefficients. Right. Okay. So here's the theorem again, given this quantity m. Here again, we can prove that actually under this assumption that the maximum principle, we can actually prove that any solution of the operator of L of u equal to 0, say in Rn to simplify, is actually, we prove quite more in that situation, which is that actually on each sphere there's at least one point which is at least precisely exponential of CMR. So here we do have exact, even we have sort of an exact lower bound. And actually, we don't just prove that lim sup S6 goes to infinity. Actually, we prove that on each sphere there's at least one point. That, and what's interesting too is that stronger form of the Langevin conjecture is actually the assumption of the maximum principle on bounded subdomains is necessary for this stronger form, not lim sup, but sup on each sphere. It's very easy to give actually counterexamples. For instance, the function, this function exponential minus x cos x is such that it solves some uniform elliptic operator equation. The eigenvalue of this operator on sufficiently large subdomains of R is not positive, right? It's negative. And this function is not such that on each sphere it's exponential, right? Because there's always subsequence going to infinity on which the cosine vanishes. So it's like the conjecture itself is true. The lim sup of modulus of u is exponential, but not sup on each R. So you see that even shows how hard it is to prove the full conjecture, because there's a big difference between lim sup and sup on each sphere. Lim sup is right. Okay, and well, only deal the proof of that. So we actually can construct, it's a solvability result. We can construct a solution which has a sign of our equation. And since it has a sign, to it applies the Harnack inequality. And we now have a sharp Harnack inequality, sharp constant, which tells you that this positive solution psi decays itself, but most exponentially. But then, if our solution is our initial solution decayed quicker, it can be squashed with the psi, right? You just make comparison to u or minus u and any constant times psi on large balls. And so u would be smaller than delta psi for each delta if you go to infinity comparison principle. And so u would be 0 because it's very for each delta. So that's again the idea. And yeah, so to summarize what we got to now, this is a work we published with Philip 2 years ago. Yeah, so this it's an approach based on optimized Harnack inequality, which, for instance, unifies the treatment of these two very classical problems: the strong maximum principle and Langevin conjecture, to which no relation had been found before. And it extends to unbounded coefficient, the numbers of coefficients, a number of situations where results were known or equal bounded coefficients. And it has even a few more advantages, such as it can treat simultaneously equations in divergence or non-divergence form, simply because it only uses the Harnack inequality, and it's a common feature for both types of equations. And the proofs are not very long once you have them. Right. So okay, so let me now move to a couple of results related to that, which are very recent, and concern optimization of constant in other types of elliptic estimates. Well, here's the thing. Actually, it's again the base motivation is the Landis conjecture, and the result by Lobalk and Pierre two French mathematicians that was published last year, says the following. Take this equation here, quotient plus div of du plus c of u, this very particular equation, right? With bounded coefficients, only bounded coefficients, and some sign on the zero order coefficient sign condition, then we can get a little bit even better result than what we had, what we knew before. We are not just able to prove that the maximum of u on each sphere is bounded below by a negative exponential, but even the average of u on each sphere is bounded below for a negative by a negative exponential, right? So it's a strong form of equivalence conjecture. Now, how is that proved? Well, it's essentially based on a duality argument. I mean, you multiply equation by something clever, integrate by parts, and if you get some terms which depend on the gradient of u, and if you are able to prove the following theorem, which per se is very interesting, but if you're able to prove the following theorem here down here, which is what? It takes a non-divergence form operator with Laplacian second order operator with bounded coefficients, coercivity assumption on the zero order term, and you look at the Dirichlet problem in some volume. Then it is absolutely classical that there is an upper bound for the gradient of the function. This is basically the theory. There is an upper bound on the gradient of the function of the solution of this problem in terms of the right-hand side f, right? But actually, the question is about an optimal constant there, and it turns out that the optimal constant is again this exponential mr in this gradient test. The optimal constant, the exponential of mr. Once you prove this, essentially this first theorem on the one-disk conjecture is more or less obtained by integration by parts of evaluated terms. Yeah, so now once more about this. Now let's talk a little bit more about. Obviously, this is very important in itself. You optimize the constant in the classical C1 estimate for the Dirichlet problem. Just let me, these two problems, the first portion u plus du and the second problem for portion of v plus b times d phi, the point is that they are dual, right? So that's the relation. Okay, so let's go back to this thing here, yeah. The proof that was initially given by this result by Lobach was based on sort of a, as they call it, differential Harnack inequality, or a log gradient estimate, which is the following. The following the result that was essentially proved by Koenig, Silvestri, and Wang, and extended by Kevin K. and Lobach recently, which is a following thing. Now, assume we have a solution, a positive solution of the homogeneous equation in some domain, say bounded coefficients, with bounded coefficients, then the gradient of log of that function is bounded. So the gradient, if you compare the gradient of the solution to the solution itself, this is bounded by a constant. Well, that's known. But the point is that this constant is precisely m. Again, just the norms of b and c. M is norm of b plus square root of norm of c in this situation. So actually, it's not just exponential. There is a very nice cancellation between the gradient of the function and the function itself, which makes that it's bounded above only by m. And once essentially if you have this thing called the psi function, you can use that psi function as a multiplier for the equation on v. You can replace v by v over psi, and you simplify the equation. And then actually there's another argument which is pretty hard again to prove the gradient bound based on doubling of variables, which is a technique useful, for instance, in the viscosity theory. Well, so one first thing we wanted to check was the following: is there an easier proof of this gradient bound, which is based on optimizing constant directly in the estimates? And actually, yes, there is an easier proof of that. There's an easier proof of that gradient estimate, which is the following. First, take only the C1 to C0 estimate, not just the standard estimate, which relates maximum of the gradient to maximum of the function itself, possibly the right-hand side. This is not so. If you optimize this by using our method with Philippe, you get some sort of polynomial dependence in the M quantity. But not, of course, this is not what we want, because now we need to still optimize the supremum of V in terms of F to get the full gradient inequality. Yeah, but this equation here, a function of V plus B dV, is actually also in non-divergence form. And for non-divergence form operators, there's a very classical estimate called the Alexandrov-Backelmann or Alexandrov-Backelmann-Pucci estimate, which, thankfully, comes already with an optimized constant. And this AVP estimate, which is it's actually a very precise estimate, which relates the maximum of a solution of a non-divergence form equation to a Lebesgue norm of the right-hand side. And here, the very proof already generates the optimal constant, which is some exponential. So if you combine these two vast inequalities here, you get the theorem above with a simple. Okay. Now another question. Now, obviously, one may ask, okay, but here we use that there was something in non-divergence form. How about the general divergence form operators, which cannot also be written in non-divergence form? So, well, then this ABP estimate needs to be replaced by the corresponding estimates for divergence form operators, which actually quite ancient. Yeah. The so-called Stampakian inequality, Stampakia-Trudingen inequality, which is in its simple form is if we have a solution of the Dirichlet problem and the problem is sufficiently coercive, let's say zero-order coefficient has a sign, then the maximum of the function is bounded by constant times the Lebesgue norm of the right-hand side in the equation. This is, for instance, a theorem.
Sorry, but yeah. Someone raised their hand, Hector Shanglara.
Okay, yeah. Hector, would you like to ask a question?
No, he just raised the hand.
Probably he's not authorized to unmute himself.
Okay, okay.
You should authorize that.
Yes.
Hector.
Hector? No, maybe it's nothing. So sorry.
Yeah,
we
can come back to a question, of course, later. Yeah, and right. So yeah, so the question now would be in that Stampakian inequality, in this basic result, what is the optimal constant of what is the optimal dependence of the constant again in the first zero-order coefficient and the size of the domain? Actually, we were quite surprised to realize that this is an open question. And well, what's happening if we examine the classical proofs of this inequality, say, for this particular operator? We see that we get an exponential of a power of Lebesgue norm of B. And this power is, the expected power here should be 1, while the known proofs gives powers which actually even bigger than 2. They are precisely 1 plus n over 2 if Q is infinite, for instance. If we just have a bounding coefficient. So actually, there's no optimized constant here. And that's a recent result we have with Philippe. Under additional assumption, which at this point we do not know how to remove, that that actually we don't just have a C0 estimates for the equation, just not L infinity, but we have C1 estimates. Assuming C1 estimates, we prove that this sigma can be taken to be 1, and then of course since we can even prove more that there is a Lipschitz estimate. So here's a theorem. Here, well, we need to start with, we need to put some condition which tells you that the operator is coercive, right? That there is a maximum principle, uniform maximum principle. One way of doing this is assume that in some larger domain, the first eigenvalue is non-negative, so that in BR it's strictly positive uniformly in terms of this couple. Just one way of saying that the one is uniformly bounded below. And then if we have a subsolution, this subsolution is bounded above by precisely what you would think, what we expect. That's that even we have a Lipschitz estimate, even have like the constant times LQ norm of the right-hand side times the distance to the boundary. Think of, say, kappa equal to 1. For the one is conjecture, you have even Rn, co-Rn. And then you get this, and automatically then if U is, by what we already know, if U is a solution of the Dirichlet problem, then we have a C1 estimate with an optimized constant, which is again the CMR. Okay. Now, this result is proved again by using duality, by using integration by parts, and another boundary, another version of the Harnack inequality, the so-called boundary, so sort of a boundary Harnack inequality, but it's more like Harnack inequality extended up to the boundary. A result, an optimized version of a result we proved with my student Fiorello Rendon and Mayra Suarez last year, which says that actually the Harnack inequality as I wrote it can be extended up to the boundary of the given set if we replace the function by its fraction by the distance to the boundary. Now, this is a C1 result, right? Because infimum of U over D on the boundary, for instance, is the gradient, right? So it's a sort of a inferior bound, or it's also a quantification of the Hopf lemma, right? If U is positive somewhere, then U over D is positive everywhere. U is bigger than constant times the distance to the boundary. And that's like the quantified Hopf lemma for super solutions. The fact that we can optimize the constant in this inequality, combined with the duality argument, leads to this result. Okay. That's and since I spoke of a Hopf lemma, there's a quite classical nowadays result that became very popular after work by Brzis and Cabré in '95, which is a sort of a quantification of a Hopf lemma in terms of a right-hand side, which is positive and not zero. So we have a super solution, positive super solution of a homogeneous inequality with a right-hand side, which is positive but not zero. Then by the strong maximum principle, the U function here must be uniformly positive. And actually, it turns out that the constant is bounded below by integral times of f times the distance to the bound. It's possible to see that this is optimal. Yeah, there are several extensions to a little bit more general operators, but not too much. So one thing we can prove is that actually the same result is valid for arbitrary operators and super solutions. And now the optimal constant in terms of the operator is again exponential. And also we have a generalized version of the differential Harnack inequality, which I recall here again is the result I came about. We can extend that to up to the boundary again, and not that much time, but just presenting here results that come up to the boundary, and general operators with unbounded coefficients again, which is again new. our previous result were concerned, and also even equations with the right-hand sides. I think that this is exactly where my time is over, so I thank you for your attention. And again, for the invitation.
Okay, so thank you very much, Boyan, for this very nice talk. So now we open the turn for questions. So maybe now Hector can, yes. So he just wrote here.
Can you hear me?
Yes, please, go ahead.
I can hear.
Awesome. Hi, Boyan. Thank you very much for your talk. I have a couple of questions. So in Lebesgue theorem, you were using the L infinity norm.
No,
but,
the Lebesgue could prove it only for L infinity functions.
Okay.
Of course, now this other proof we have gives the L norm.
Okay. Awesome. So another question. So this is zero constant, no? It depends also on the ratio between the ellipticity constants, no?
That's correct. Yes.
So will it say something interesting to optimize this dependence as well?
Well, but that's another line of research. I mean,
okay.
There are people who have studied that. Actually, this is known.
Okay.
For divergence form operators like divergence of AX du, this is, for instance, very deeply studied. I mean, I think that the best result that I saw was some result by Dolbeau and other people, which gives a very, very precise evaluation of, it's a sort of an explanation of a gain of lambda over lambda. And for non-divergence form operators, as you probably know, it's still an open question that people are working, and there's a progress. But that's another line of progress. I mean, optimizing C in terms of lambda over lambda is another question. And of course, these two can be gathered together.
But will it say something relevant for the problems that you are studying, or
No, for the problems we're studying, not really, because I mean they are more. I mean, that's there the ellipticity is considered fixed. What you want is like get more general results in terms of the other coefficients, right?
Okay.
But this doesn't mean it's not interesting in itself. It's extremely interesting in itself. The dependence in the ellipticity.
Thank you.
Okay, is there any other question? So I have one. Okay, so the results by Koenig one, they assume some sign for the potential, right?
Yes.
Okay, and then the recent result by Malenikova,
That's right.
Lugunov, it does not, right?
Exactly.
And where your result is between these two kind of results, because you assume
our result is well, we do not assume a sign.
Yeah.
We assume a little bit weaker, assuming only the, let's say, the positivity of the first eigenvalue.
Yes.
But above all, what we can do is we can consider coefficients which are unbounded, and that they cannot.
Yeah. Okay. But I mean, in some sense, you may consider problems where the potential there is no sign, right?
Of course, yes. But still, there is a coercivity in terms of the positivity of the first eigenvalue.
Okay.
That's right.
Okay.
But what's even more is that we can assume that we can have coefficients which are even locally unbounded. I mean, that's just integrable. Even
okay.
Locally.
And you also can consider stereo domains, right? As you said.
Yes.
And there is any assumption on the regularity of these domains, or
absolutely not. No, but there is an assumption of sign on the function on their boundary. But the regularity is arbitrary, essentially.
Okay, that's very good. Okay, there is another question by Mohamed El Aide. Please go ahead.
Yes, thank you. I am asking with a continuation of this work. Can we apply the results for the B Laplacian operator with the switchable boundary conditions? This is my question.
The viewer portion with some special boundary condition.
Yes, I am asking whether we can apply your result for the B Laplacian or for another kind.
Well, I would expect it to be applicable to say viewer portion with the so-called Navier conditions, because then it is possible to write the viewer portion equation as a solution of a system of equations. And they are Harnack inequalities for some systems. So then these Harnack inequalities, those Harnack inequalities could be optimized again with respect to the.
I think that we must add additional boundary condition in this case.
Yeah, of course, yes. There would be, for instance, if you have a viewer portion equation, we would have to have a boundary condition both on the function and the portion itself.
Thank you very much.
I mean, it's not done, but I would expect it.
Okay, is there any other question? So if not, thank you very much, Professor Boyan, for this very nice talk. It was very nice. So now I pass the word to Brian to end the session.
Okay, thank you, Professor Sousa. Thank you, Professor Boyan. I think, okay, there's no more questions. I want to thank you very much to everyone for attending today. I would like to make some announcements. First, I want to thank our speakers for today, Professors Felipe Linares and Boyan Sirakov, for giving us these fascinating talks, and our collaborators, Professors Michael Cardoso and Diego Sousa, for chairing this 4th day of conferences. Tomorrow, we will conclude this event with a talk by Professor Enrique Suazua, and we're having a short closing. Also, I want to announce that thanks to the support of the Ghent Analysis and PDE Center and the book series Trends in Mathematics by Springer, we will be releasing a volume linked to this event, to the ICMAM Satellite Conference on Analysis and PDE. All of our speakers and participants will be invited to submit a contribution to this volume, which will consist of extended abstracts of ongoing research related to the topics of this conference. We will send emails with more information in the near future. If you have any questions, do not hesitate to contact us. And thank you for attending today again, and see you tomorrow. Bye-bye.
Okay, bye-bye.